Now we've just seen that component form is a really handy way of breaking up the horizontal and the vertical parts or components of any vector. But it can be a little bit clunky dealing with all of those terms when you've got x's and y's and i's and j's all over the place. So another way that we can write the exact same thing is using column notation. Now, any vector that we can write in component form, we can just take the part that tells us how far we're moving horizontally and put it on the top, and the part we're moving vertically and put it on the bottom, and we use square brackets. We don't use round brackets here because then there's a danger of them looking a little bit like the choose numbers that we saw in our combinatorics unit. So the square brackets are the go. And this means that we'll write our basis vectors I and j like this. If I is deemed to be one unit that we're moving to the right in a positive direction and we're not moving up at all, then we'll write it like this. Whereas the vector j says that we're not moving left and right, we're just moving one unit up. Now, when you're using column notation, it's a really handy way of being able to add vectors together or multiply them by a scalar quantity without getting confused with all of the terms. So here we have two vectors being added, and all we need to do is add the horizontal components and put that on the top, and add the vertical components and put those on the bottom, and put square brackets around the whole thing. And if we're multiplying a vector by some scalar quantity, it just means that we need to multiply the scalar quantity by both the horizontal and the vertical components. So that's quite straightforward. Now we can also write vectors as the sum of basis vectors. Now I'm not sure why you'd want to do this a lot, because it's taking the advantage of the column notation and actually making it a disadvantage by breaking it back up again, but I suppose there could be a use for this further down the track. Our early questions won't have us doing this so much. But you can see here that if our basis vectors are these, then we can see that any vector that's written in column notation, we can take that number and say that's the multiple of this unit vector, and this number here will be the multiple of that unit vector. So we've got two vectors here, and we need to find a range of things. Now these three will be vectors in their own right, and these two, with the absolute value brackets, are saying what is the length of those vectors. So the first one, we need to add the vectors together. Now, when you start doing this, feel free to use the working, and then if you can do it in your head and you're not getting them wrong, by all means do so. So in big brackets here, we need to do 2 plus -3, and on the bottom, we've got 5 plus 1. It's as simple as that. So our answer is going to be -1, 6. Now, you could write it out like that. You could write it like this with a plus in between. I haven't quite left enough room to do that. So whichever way you go is fine. You might jump straight to this once you get the hang of it. But just be careful not to make sign errors. Here we need to do v minus u. So I'm going to need to have -3 minus 2. I can do that in my head. And then I need to have 1 minus 5. So that's a -4. Okay, the absolute value of u, well, that's saying how long is this vector. So I'm going to need to draw it. So a quick sketch here tells me that I need to go from an origin 2 steps to the right and then 5 steps up. So I've got a triangle that looks roughly like that, and this is vector u here. So what would Pythagoras say about this? We've got a right angled triangle. We've got 2 squared plus 5 squared will equal this side squared. So I've got, what's that, 25 plus 4, I've got 29, and the square root of that, I can see that this side is going to be the square root of 29. So that will be the length of that vector. Now for the next one, there's a few ways that you could set this out. You could work in your head. I'd advise some working, especially when you're starting. We need 2 lots of this vector minus 5 lots of this one. So effectively here I've got 4 and 10 as my components. But making it sure that I don't make a sign error, it might be best to add here and say that I've got, because I've got -5 times -3, I've got a 15 on the top of this one. And here I'm subtracting 5 times 1. So that means I need to either subtract and then have the 5 there, but now that I've decided to add, I'm going to need to put a -5 in here. Does that make sense? So bringing that all together, if I'm adding the vectors, the 4 plus the 15 gives me 19, and the 10 plus -5 gives me 5. We get that. Now, if you were going to do it in your head, just got to be careful. You'd need to say, I've got 2 2's, that's 4, minus 5 of those, so minus 5 negative 3's is plus 15, and you could say I've got 4 plus 15 and go straight to the 19, but I recommend some working is a good idea. Now here, we're trying to find the absolute value of this vector. So here's the vector. We need to use that and think, well, what set of directions does that vector give me? If I start at some origin, O, I need to go 19 units to the right and 5 units up. So I have something like, looks like this, and this is the vector in question, 2u minus 5v. So again, using Pythagoras, I need to say that 19 squared plus 5 squared is equal to, we can just call this c if we like. So c is going to be the square root of that. And I can put that into my calculator, and that will be the answer to that question.